So today I will continue the lecture series with calculation of the equation of state. I will discuss SU3 gauge theory first as kind of a warm-up example. Then I will discuss the Taylor expansion of the pressure in terms of the chemical potential. And then in this section I will focus a little bit more on the comparison of the lattice results to Hadron Resonance Gas model, as well as to V-coupling expansion. And towards the end, I will discuss QCD equation of state at non-zero baryon density. So let me start with the equation of state. So the basic challenge in calculating equation of state is that, of course, we cannot calculate the free energy of QCD directly, or the partition function, is simply because we do calculation using importance sampling, and the probability measure in this importance sampling has a normalization uncertainty that we don't know. However, what we could easily calculate is the derivative of the logarithm of the partition function, because in this case, essentially, it boils down to calculating expectation value of some operator. So if you just take the standard path integral of the logarithm of partition function, then taking the derivative, you see that you get the expectation value of the gauge action upon taking the derivative, and the expectation value of the gauge action is something we could calculate. Now, if you want to calculate the pressure, now you have the derivative of the logarithm of partition function, so now you have to integrate in order to calculate the pressure. So then you could do the integration in the bare coupling beta, so that is gauge coupling, from some initial value, beta 0, to a value of beta, which corresponds to the temperature interested in. Of course, you want to choose this beta 0 to be small enough, so it corresponds to a small enough temperature that the pressure at T0, which corresponds to this beta 0, is essentially 0. And therefore, what you get is the integral of the expectation value of your gauge action integrated in beta from some beta 0 to beta tau. Of course, the plaquette itself has all kind of ultraviolet divergences that you want to remove. So essentially what you have to say that you measure the pressure with respect to the vacuum pressure, so to say. So what you calculate is the difference in the expectation value of the gauge action at 0 temperature minus the gauge action at finite temperature, and integrate it over, so that in that combination, the ultraviolet divergences cancel. Of course, once you have the pressure, you could take the derivative of the pressure to calculate the entropy density or the energy density and all the other quantities using thermodynamic relations. Since you're calculating the derivative, for example, when you calculate the trace anomaly, what you have to do is to calculate the derivative of the pressure divided by T to the force with respect to the temperature. And then what shows up is actually the derivative of your gauge coupling with respect to the temperature, which is equivalent to the derivative of your gauge coupling with respect to the lattice spacing. So here you see that that's nothing else but essentially the lattice analog of the wave function. So here you need to know how fast the gauge coupling varies as you vary the lattice spacing. So that's essentially the non-perturbative beta function, if you wish. And then, of course, you have the derivative of the pressure with respect to beta. Now, one of the problems in these computations that you have to calculate the difference between the gauge action in the vacuum and the gauge at the finite temperature. As you go closer to continuum limit, this difference becomes smaller and smaller. So in overall, you need to calculate both of these quantities very precisely, and therefore the computational cost as you go closer to continuum increase as n tau to the 4 because of this. You have to calculate this difference. Now, of course, if you calculate any thermodynamic quantity, you have to be aware of cutoff effects. When you, so what I show here is a trace anomaly, so epsilon minus 3p in T to the 4th unit calculated different cutoffs, so different n tau, so n tau equal 4, n tau equal 6, n tau equal 8. And you see the height of the peak in the trace anomaly decreases as you go closer to the continuum limit. So eventually you have to extrapolate all these results in 1/n tau squared to get the trace anomaly and then the pressure in the continuum limit. That has been done for pure gauge theory a long time ago, and that's now an iconic figure. So here I show the pressure calculated for different n taus, 6, 8, and 6, 4, 6, and 8, and eventually from that you can get the continuum estimate. What you could also see is that when you're calculating the cutoff effects in pure gauge series, they typically tend to be much larger. So in other words, the cutoff effects that you infer from free theory typically are much larger than what you get in interacting theory. So once you do the continuum extrapolation, you could calculate now all the quantities you're interested: energy density in unit t to the fourth, entropy density in unit t cubed, and the pressure, 3 times the pressure, and they are shown here. So of course, as a phase transition, you have a big jump in energy density, which is indicated by this bar, and then you approach the high temperature limit as you increase the temperature. Now, so that was with a standard action. If you use improved action, as I explained its advantages to doing this calculation, then you could reduce much, to a large extent, these cutoff effects. And that is shown in this figure. So here I show the pure gluonic pressure calculated for different cutoffs. For n tau equal 4 is 1/1 action, so that's a standard gluon action, so only plaquette. And then n tau equal 4 with improved action. And I also show the continuum result, which is essentially the identical curve from here. And I show the n tau equal 4 1/2 also now tadpole improved n tau equal 4. And you see that the improved result, improved action already with n tau equal 4 seem to be pretty close to the continuum result. So even if you do the coarsest lattice with improved action, you get much reduced cutoff effects. So now with that, you could look at the calculation in full QCD. So now I'm showing results in 2+1 flavor QCD. So the idea is the same. You calculate the derivative of the free energy or the pressure itself instead of calculating the pressure. So you calculate the trace anomaly again. You express it as derivative of the pressure, and then you integrate the trace anomaly from some reference temperature T0 to the temperature you're interested in order to get the difference in the pressure. Now this first term, you try to make it small, so by choosing the temperature to be small enough, so you could either set it to 0 or estimate it just using a hadron gas calculation. Now if you take the derivatives at the level of the path integral, then you get an expression which is the same as before. So you have the difference in the gauge action at 0 temperature, at finite temperature, the non-perturbative beta function, so the derivative of the gauge coupling with respect to the lattice spacing A. And then, of course, in addition, because now you have also dependence of the quark masses on the lattice spacing, you get this product of the beta function and the running mass Rm, which essentially tells you how the bare quark mass that you have to put in your lattice calculation change with respect to the lattice spacing with respect to beta. So this function, of course, is something you have to calculate. So you have to do the corresponding 0 temperature calculation in any case in order to subtraction. And from the 0 temperature calculation, you could infer what is a running quark mass that corresponds to a given constant physics. So what quark mass gives you the physical pion mass as you vary the gauge coupling. And of course, the same thing, you know the scale, lattice spacing as function of beta when you do the 0 temperature calculation. And eventually you have to interpolate those results. So here I show the non-perturbative beta function as function of the gauge coupling itself. So large beta that's closer to continuum limit, so closer to the V coupling. And I compare this result with a naive expectation, so to say, the asymptotic 2 beta function. And clearly, when you have small lattice spacing, which means a small temperature or small n tau, then you're very far away from the perturbative beta function. But eventually, as you go closer to the continuum limit, your non-perturbative beta function tends to approach the 2 beta function, as you would expect. Now, for the running quark mass, you have a similar situation. So you tune your quark mass such to get the meson masses to be the same, to be as close to the physical value as possible. Of course, you do it by trial and error. So in practical simulation, you have to have chosen the quark masses according to the thread line. Of course, when we do calculation, try to get the quark mass, we not always able to fine-tune it. So the actual simulation data is shown in this blue line, but eventually we know how to correct for it. And then we estimate the correct lines of constant physics in terms of the quark mass as function of beta to be these red points, which then we interpolate. And once we interpolate around those points, we could calculate the derivative of the quark mass with respect to beta. Again, if you go to high beta values, perturbation theory should apply. And eventually you should get the leading order anomalous dimension for your quark. And that is shown here by this horizontal black line. Now, if you put everything together, you could essentially get lattice results for the trace anomaly at different lattice spacing for different tau. And here I show the calculation done with different action and different lattice spacing. So the colored symbols are the contemporary results using the highly improved staggered quark, the HISC quark action. And in the black dots or black symbols are the earlier calculation, which were done also with improved action, but less optimized one. And you see that if you don't use the most optimized action, you're very far off in terms of where you should be. So the trace anomaly, unless the action is highly improved, becomes very large around the transition region, around temperature 200 MeV. Well, actually, it's below the transition, and actually below the transition is too small. So somehow the entire curve, if you have large cutoff effects, is off by a large amount. So even unless you use the most improved action, you could imagine getting the continuum results for the trace anomaly is extremely challenging. So with the HISC action, it was possible. And in fact, in the HISC action, what you see is that except for tau equals 6, all the lattice spacings are pretty much on top of each other. So doing the continuum extrapolation is relatively easy because you don't have much variation with the lattice spacing. As you go to high temperature, it means, again, fine lattice spacing. Actually, even the less optimal action, like the A squared and P4, seem to follow the same trend. So at about 300 MeV, all the action actually gives consistent results. So here, discretization effects actually become quite small. Now, if you have these results, you need to perform some spline interpolation in order to have a smooth function that you could integrate over. So we perform spline interpolation using all tau equals 6 data, such that the coefficient of the spline take into account the leading order cutoff dependence of the lattice results. So the coefficient of the spline has typically a form like A plus B n tau squared. And then, of course, you can do a simultaneous spline fit of all the variable lattice results. Moreover, you have to constrain the fit to get a stable fit such that it smoothly matches to Hadron Resonance Gas at some low temperature, which we chose to be 130 MeV. Once you get a spline, you could do the interpolation, so spline interpolation, you could do the integration in order to calculate the pressure. And from the pressure, you could then calculate also the entropy density and energy density. And here show the final continuum extrapolated results for different quantities. So here I show the trace anomaly itself, and I show this 3 times the pressure, entropy density, and energy density functions of temperature. And all these calculations are compared with the Hadron Resonance Gas, which I discussed in the first lecture. So what we do here when we try to estimate the thermodynamic quantities in the Hadron Resonance Gas, we simply take all the particles and all the resonances from particle data group PDG, and treats them as stable, absolutely stable particles at a zero width in ideal gas approximation. So that's adding all these particles in the ideal gas formulas and gives the Hadron Resonance Gas curve, which are shown here as well as here. And what you see is that in the low temperatures, the Hadron Resonance Gas describes the data very well. Actually, it follows the trend even at to some extent, even at temperature higher than the transition temperature, which is seems to be a little bit odd at the first sight. Now, the transition temperature or the transition region is marked by this yellow band, and you see that all these thermodynamic quantities, the pressure, energy densities, they change very smoothly across the transition. So it's really very hard to pinpoint where the crossover temperature should be if you just look at the pressure or energy density, because there's a variation extremely smooth. Now, if you try to estimate what is the energy density where the transition happens, so you just plug in the transition temperature and use the value as equation of the energy density at that point, then you estimate the pseudo-critical energy density to be 420 MeV with an error of 60 MeV per Fermi cube. And that's something that you could compare with the energy density in normal nuclear matter, which is about 150 MeV per Fermi cube. So that's energy density is about 3 times the energy density of normal nuclear matter, and it's actually close to the energy density inside the proton. Now, it's important, of course, to say that this calculation is not the unique. So the other group, namely the group in Wuppertal, using a different discretization effects, did the same calculations. They extrapolate the continuum results. So it is an important cross-check for all lattice calculations to compare different continuum results. And this is shown in this figure. So the colored band of the calculation I just described using the highly improved staggered quark action by hot QCD collaboration, and the gray bands are the calculation by Wuppertal group done using the stout action. And what we see that for all the quantities, we have a pretty good agreement between the two calculations. It should be. So in the continuum limit, it doesn't matter which lattice discretization you use. If you do the calculation properly, you should get the results. So with an error band, we indeed see that the results agree. I also show the speed of sound squared as function of the temperature. And what's interesting is that at low temperature, it agrees with the Hadron Resonance Gas result shown as a black line. And then the speed of sound slowly approaches the value characteristic for ideal gas, which is 1/3 the speed of sound squared, but it does so very slowly again. And moreover, you never get a small speed of sound, even if you go closer to the transition point. The equation is never really soft. The equation state is never really soft. The speed of sound is actually seems to be quite significant. Now, this calculation have been extended recently to much higher temperatures. So now we are talking about temperature which range from the transition temperature up to 2 GeV. And if you go to this high temperature region, the one question that could be asked, to what extent does this calculation agree with the V-coupling predictions? So here I show 3 different quantities. The energy density, the trace anomaly, so epsilon minus 3p in t to the 4th units, compared to V-coupling calculation done in 3-loop half-thermal perturbation theory. This is this red band. The lattice data, obviously, the black dots. The band essentially corresponds to, so there is a central value which corresponds to some scale choice, which is 2 pi t, so the canonical scale choice, and then you vary the renormalization, say, by factor of 2, you get this band, and within this band, the lattice data seem to agree quite well. There is also another calculation that use electrostatic QCD, which I introduced in the first lecture as well, that's shown as a dash band, and that again seems to be in reasonable good agreement with the data. Yes? Yeah, I mean, it's accident, right? I mean, the EQCD band, if you, I showed it's a line because that's how it's published, but also is that it's a band. So I guess as long as it agrees with uncertainty, it's fine. And even if it does not, I mean, then of course you could make questions whether the uncertainty was close enough, conservative enough, right? Because in principle, there are two ways how you estimate a perturbative. So that you vary the scale that gives you sensitivity to higher order corrections to some extent, but in principle, you could also think whether there's some additional correction, like power law correction, non-perturbative correction, which are not taken in account. For example, none of this calculation takes into account the full g to the sixth term, which is non-perturbative. So in EQCD, essentially the value of this g to the sixth term is guessed based on pure glue calculation. In HDL, 3-loop HDL, it's ignored at all completely. Right? So it's the red line is the HDL, the central value, and the band is a scale variation of that red line. So that's a sort of say the perturbative uncertainty. So you could also look at the pressure. No, it probably exists, but it was not published. At least yeah. So not in the form that I could use, at least. It exists in some form. So here I show the pressure divided by the ideal gas pressure. So of course, if you go to infinitely high temperature, it should go to 1. Now actually, at the highest temperature, which is 2 GeV, is not too far from 1. It's about 10% below 1. So you may say that the effect of interaction reduces the pressure at the highest temperature by something like 10%. At the lowest temperature, it's probably more like 20 to 50%. And again, you could compare different calculations. So the red line is again the hard thermal loop. So you have the red line, and then the band, again, the scale uncertainty for varying the scale by a factor of 2 around its central value 2 pi t. I show the EQCD line as the dashed line, and now it turns out to be a bit higher than the lattice, but again, the deviations at the percent level. And there is another perturbative scheme that was invented by Tony Rephan, another type of resummation, which is called next to leading log approximation. And it's also slightly higher, but not, it's basically within the error band of the lattice result. And finally, I show the entropy divided by the ideal gas entropy. And again, you see the same picture. The EQCD line is higher, but the other two resummed calculation more or less agree with the lattice results. The HDL, 3-loop HDL, actually has a large uncertainty band, and with the uncertainty band, it always agree with the lattice results for temperature larger than 400 MeV.
Do you think that if you go higher loops, that gap will go away for hard thermal loop calculation?
Yeah, I mean, ideally, I mean, first of all, one needs a realistic uncertainty of what's the error, right? Because as I said, here's the g to the sixth term, which is non-perturbative, was essentially just guessed, so it was not calculated. In the blue line, it was ignored, and in the blue band, it was ignored, and in the red band, it was also ignored. So none of this calculation is, sort of say, in some sense complete. I mean, you don't think that the g to the sixth term should be very large, but you don't know till you calculate it. Well, because the coupling runs logarithmically, right? So once you're in this regime, right? So if once the lattice data is similar to perturbation theory, then you kind of estimate when it will get 1. So essentially, this red line, despite of all its incompleteness, if you wish, is a pretty good guess how it will approach the infinite temperature limit, and it will increase logarithmically. So kind of changing the temperature by a factor of 2 won't help. You need to change it by 16 order of magnitude, or maybe more, 20 orders of magnitude till you get to 1. From here on, it's just logarithmic running, which is very slow. So this is expectations that it should be 1. It's kind of, yeah, it's certainly mathematically true, but you will never see it in practice. Yes. So G is always greater than 1, and none of these approaches a priori would be trustworthy unless we would have the lattice result to show that, in fact, they reproduce the physics. And I will show more example. So if you ask why one should believe decoupling calculation at the temperature, let's say, even as high as 2 GeV, my only answer is that because it has been tested versus the lattice in many instances, and in most instances we find. Absolutely. Right. 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 Absolutely. It's very non-trivial. Yeah, I mean, but as I said, I mean, if I would have only this figure to look at, I wouldn't convince. I would tend to say that's probably accidental because it's too good to be true. But as I will go on, and also tomorrow, you will show that this pattern repeats itself. So certain features of the lattice results of pressure and its derivatives, as well as some of this correlation function, you could very well understand in terms of EQCD, for example, which is not at all obvious given the fact that you don't have a real scale separation numerically. It's only parametric, and G is 1, so it's not applicable if EQ. It's not clear if EQCD is applicable at all, but it seems to be the case. Okay, so now I talked about temperature as high as 2 GeV. Of course, if you really have that high temperature, kind of in physics world, then already using 2+1 flavor calculation is not quite adequate, because at that scale you may worry about the charm quark effects, and that has been studied in particular by the Wuppertal group. And here I show the contribution of charm quark to different quantities. So that's the figures I took from this paper, or some version of it, but the results have been published in this paper. So here I show the trace anomaly as function of the temperature, calculating 2+1 flavor, and 2+1+1 flavor, both is continuum extrapolate lattice results, and compared with a Haas thermal loop perturbation theory, which I guess in that case was just a 3 flavor calculation. Also, I'm not quite sure because it wasn't explained in the paper. I think it's here. It was no. It's actually here. It was 4 flavor. So what you see is that trace anomaly shows some effect or some sensitivity to the charm quark mass. So already at temperature like 400 MeV, you start to see that the 3 flavor calculation and 4 flavor calculation, which includes the charm quark mass, start to differ. And in the pressure, again, the same pattern. So certainly already at temperature 500 MeV, you see a significant difference between 2 or 3 flavor calculation and 4 flavor calculation. So in fact, if you would think about the early universe where the things are in thermal equilibrium, there, of course, at temperature 400 MeV charm quarks is very important. No, I mean, the scale is different. So I guess the lowest temperature is here at 100, 120 around. I don't know what the lowest temperatures they used, but it's around 120. And if you look at the other calculation, that certainly also goes down. That always 100. 130 was kind of an arbitrary choice because that's where we said let's enter our interpolation of the lattice data match with HRG. So that's what we use as a reference point to calculate the pressure, but we have data even below 130 MeV. But of course, you cannot go very low because then the cutoff effects become too large. So remember that the cutoff is proportional to the inverse of the lattice space, or inverse of the temperature divided by n tau. So low temperature means that the lattices become very coarse. Okay, so now after we calculate the equation of state at zero baryon density or zero chemical potential, the question is how would we continue with the calculation if we want to study the effects of chemical potential? And the answer is, because of the sign problem, the most natural way to do it is to calculate the pressure in the presence of chemical potential in form of the Taylor series. So we just expand the pressure in chemical potentials kind of around zero chemical potential. Now, if you have, in general, let's say a four-flavor theory, right? So you have different chemical potential, which you could either think as being the chemical potential up and down quark, a strange quark and the charm quark, or equivalently as the chemical potential corresponding to the baryon number, electric charge, strangeness, and charm quantum numbers. And of course, those are just two bases. So in principle, these two expansions are equivalent. So you could convert one expansion coefficient into another. And now the expansion coefficient are just derivative of your pressure evaluated at zero chemical potential, and therefore they are perfectly calculable in standard Monte Carlo calculations. Of course, the calculations themselves becomes more and more difficult as you want to calculate the high derivative, but in principle, that's a well-defined calculation which can be done by a Monte Carlo method. Now, the interesting thing about this coefficient is that they not only allow you to calculate the pressure at non-zero chemical potential, but they also give you some additional insight into the physics of the Quark-Gluon plasma, because namely, they related to the fluctuation and correlation of conserved charges. So in particular, if you have some conserved charge X, which could be baryon number, electric charge, strangeness, then the second order expansion, diagonal expansion coefficient just gives you the fluctuation of this quantum number, or the off-diagonal derivatives of diagonal coefficients give you the correlation between conserved charge X and conserved charge Y. So in a way, these quantities carry information or give information about what carries as a conserved charge, whether the conserved charge like baryon numbers carried by hadrons or carried by quarks, and therefore they're sensitive to a large extent to the degrees of freedom and can probe the deconfinement properties of the medium. So here I kind of show as an example how one could think about this. So as an example, I show the baryon number fluctuations, so second order coefficient, electric charge, strangeness, as now as function of the temperature. And all these quantities, of course, I could calculate in ideal quark gas, which here it just becomes some number. So the baryon number fluctuation is just 1/3, electric charge is 2/3, and strangeness is 1. So if I normalize by this, what I see is that all the quantities, all this fluctuation calculated on the lattice in this normalization approach to 1 at high temperature, which means that at high temperature, the conserved charges are carried by light quarks, as you would kind of naively expect. At low temperature, on the other hand, this quantity are significantly smaller than 1, and that also can be understood because all these conserved charges are carried by massive hadrons. And then in between, you have this transition from one to another, so somehow as you increase the temperature, this fluctuation grow, and to a large extent that can be understood in Hadron Resonance Gas, so you could calculate all this quantity also in Hadron Resonance Gas, and to a large extent the Hadron Resonance Gas captures this trend of the lattice data, and of course at higher temperature is no longer valid, but eventually the fluctuation will saturate us in these units. So now we could also consider higher order fluctuation, in particular the ratio of higher order fluctuations to lower order fluctuation, and that also has an intuitive understanding. So here I show the fourth order baryon fluctuation divided by second order baryon number fluctuations. And this example very well demonstrates how you could understand the relation between the fluctuation of conserved charges and the carries degrees of freedom and excitation in your system. So at low temperature, of course, the baryon number is carried by baryons, so it composes 6 quarks, and the baryon number could be only either +1 or -1. So therefore, all these fluctuations, chi2 is 1, chi4 is 1, so all of these fluctuations just 1. And therefore, their ratio, if you're in hadron phase, so chi4 over chi-b is 1, and what you see from the lattice is exactly this. Now, if you go to the quark phase, and again, you treat the baryon kind of charges classically, but now the baryon charge is carried by quark, so quark has 1/3 of the baryon number, or -1/3. Therefore, the fluctuations, the second order fluctuation is 1/9, and the fourth order fluctuation is 1/81. So now the ratio of the fourth order to second order fluctuation is roughly 1/9, and that is shown as this blue line. And again, that's not very far from where the lattice results are. So what you see is that the temperature dependence with ratio of the fourth order to second order baryon number fluctuations follows the naive expectations that at low temperature it's just a gas of baryons, which with number 1 or baryon number 1 or -1, and in the high temperature just the quark gas where the quarks carry a fractional baryon number of 1/3. And the yellow band again indicates the uncertainty, the transition region. Okay, so now you could also look a little bit more in the fluctuations. So for example, you could look in terms of correlations between different quark numbers, so between the U quark and S quark, and you see that this correlation have a non-trivial pattern. They're negative at low temperature and tend to be 0 at high temperature. And again, that's something that you could explain in the Hadron Resonance Gas, which is shown in this black line. So the reason why you have this correlation between U and S quark at low temperature is because you have hadrons containing both strange and U quark, and therefore they're correlated. And the fact this pattern is just comes from the fact that here you have combination between baryons and mesons, and at low temperature, of course, the kaon is dominant. And if you have a U quark, you have you have a U quark, you have an anti-S quark, and therefore this correlation is negative. On the other hand, if you go to high temperature, if you have a really ideal gas of quarks, then U quark doesn't talk to S quark, and this correlation just should be identical to 0. You could also look at the baryon strangeness correlation, baryon number and strangeness correlation. Again, this correlation is dominated by strange baryons in the low temperature region, and is described reasonably well by the Hadron Resonance Gas. And at high temperature region, all the strange, you have strange quarks which carry both baryon number and strangeness. So namely, they carry 1 unit of baryon number, 1 unit of strangeness. Therefore, if you take this combination, where you take the correlation between baryon number and strangeness divided by the fluctuation of strangeness itself, times 3, it should approach 1 if you go to quark gas, and that's exactly what you see in the lattice results. Note, however, that this transition from hadronic description to kind of quark-like description doesn't happen instantaneously. It's kind of a smooth transition, and there is this region in temperature which is 100 to 150 MeV wide, where, of course, it's neither a quark gas nor a hadron gas. Now again, you could look at the fluctuations in the high temperature phase. So as I explained just before, at high temperatures, the ratio of your fluctuations by the corresponding fluctuation in the ideal quark gas is close to 1. So now we want to zoom in this region a little bit, understand whether this small deviation from 1 can be understood at a quantitative level using decoupling. So here I show the comparison of the lattice results, and again, the calculation have been carried at several lattice spacing, extrapolated to the continuum limit. And this continuum extrapolated lattice result are shown as these black symbols here. And now we compare again with the decoupling calculation, namely the 3-loop half thermal loop calculation, shown by the dashed line, and the EQCD calculation shown by the red band. So what I show here is the fourth order U-quark fluctuation divided by the ideal gas value, and the second order U-quark number fluctuation divided by ideal gas value in this inset. And once again, one sees that we have a pretty good agreement between the HDR calculation and the lattice results. So now you have 3 lines here, which in certain indicates uncertainty, scale uncertainty in the half thermal loop results. So the central value is 2 pi t, agrees very well with the lattice results, and then the other 2 lines as a scale operation by a factor of 2. The EQCD result seems to be a little bit higher. Now, if you go to the second order fluctuation, it's kind of vice versa. The EQCD results seems to be very close to the lattice results, and the HDR, of course, has a larger uncertainty band. Within this large uncertainty band, it's compatible with the lattice. Now you could look at the quark number fluctuations, and I showed you in the previous slide that they kind of approach 1 very quickly, they're very small, but now again, if you do a precise calculation, you can ask how small they are and whether the smallness of this of diagonal U and D correlations can be understood quantitatively. It's a non-trivial check because, strictly speaking, this quantity is not calculable in the loop expansion, so it's calculable in decoupling expansion, but not in the loop expansion because it starts at g to the 6. So it's totally non-perturbative in terms of EQCD, but if you do a non-perturbative EQCD calculation, you actually can find what it is, and that is shown as with this, again, this red band overlaid with a continuum extrapolated lattice result, as well as the lattice results at different lattice spacing, which are colored symbols. And again, we see that the lattice results, the continuum extrapolated lattice results, agree very well with the uncertainty band of this EQCD result. So that's probably one of the most non-trivial tests of EQCD so far, whereas you have something which is strictly perturbatively 0, so in the loop expansion, but you have a non-trivial contribution, non-perturbative from EQCD, which can be tested, and it agrees very well. Okay, maybe at this point, I stop for a minute and ask if anyone has a question, because I'm switching gears a little bit. To some extent. Now, of course, you need to keep in mind that HDL, this separation, so EQCD, you must have this separation between the Debye scale and 2 pi t, right? Now, the idea of the screen perturbation theory and to some extent the HDL perturbation theory, that maybe that's too restrictive and you don't necessarily need to have that. Then of course, the question, but then of course there you have no way to systematically incorporate non-perturbative effects. So it resumes some perturbative calculations that EQCD cannot do, because perturbatively you don't necessarily have to assume the scale separation between 2 pi t and md, so GT. So that's the philosophy of, but then of course you have no way to incorporating the physics of magnetic sector.
Can one imagine quantifying the differences from EQCD in a systematic way? So the breakdown of dimensional reduction, for example, an expansion, say, in MD or 2 pi t.
It's strongly quantity dependent. For the pressure, from what I could tell, is not too bad, but where it probably breaks down is a Polyakov loop expectation value, for example. There you need to go like to 20 TC to get.
Right.
I will show that when too close to the result.
What I'm saying is a numerical observation, but I'm saying, can one, so for each of these quantities, do a systematic expansion in the quote-unquote breakdown of EQCD sort of essentially quantifying where it becomes more reliable or
yeah, I mean, it probably could be done, but I mean, nobody did a very thorough analysis of that. So it's probably one could improve in understanding, right? For example, I mean, if we somehow stuck with this idea that perturbation theory has this poor convergence, despite that we went to very high order. Now, if you look closely, we never went to very high order because 3-loop is all what we have. In some cases, we have 4-loop. And of course, if you neglect the 1-loop correction, which is to some extent is a 3 level, you say, well, we're talking about convergence in having 1-loop and 2-loop. And of course, that's all what we have. So it's a lot of things that needs to be kind of, well, first of all, one needs a full loop or 4-loop calculation. So when you, at least you have the 2-loop running coupling or constant effects in the pressure. And that's of course, a very challenging calculation. It can be done in principle. And then of course, you could try to think about systematic studies that you have in mind. Yes, Sayantan.
So when we have purely gauge bosons, then the convergence to perturbative estimates is very slow. But when we have fermions, it seems like it.
Well, I mean, the bosonic part is always there, right? It's just not. Then you add something which you may hope to be more perturbative, right? So the relative contribution, which is of problematic part in full QCD is smaller, so that of course may explain. Now, of course, the other thing is that we are talking about here purely quark observable, so gluons don't contribute explicitly on this loop, so that also helps. But in the pressures they do, so the fact that you have both the pressure and this is working is to some extent non-trivial because it tells you that also gluons at high temperatures for bulk thermodynamics, they kind of behave as you expect. Okay, so now let me kind of continue with the fluctuations, but we kind of try to understand a little bit better the low temperature part of these fluctuations, where I argued that it's kind of can be understood in Hadron Resonance Gas. So I will try now to scrutinize a little bit what happens at lower temperature and to what extent we could understand it Hadron Resonance Gas. So if you, and one important example which we understand reasonably well right now, or at least better maybe than other sectors, is a strangeness. So when you think of a strange contribution to the pressure, and you think of a simple hadron gas picture, you may say that the strange, partial strange pressure can be decomposed into partial pressures due to strange mesons and strange baryons, and then strange baryons come, of course, with strangeness 1, strangeness 2, or strangeness 3, so that's omega, there's a cascade, and that's the hyperons. And if you really deal with heavy particles, some particles which have masses much larger than temperatures, and of course the Hadron Resonance Gas itself becomes simpler, in a sense that the temperature dependence and the dependence on the chemical potential can be factored out. So typically you can always write the pressure as some term or some piece which only depends on the temperature. So that essentially would be the partial pressure at 0 chemical potential. And then dependence of the pressure on the chemical potential is always given by some cosine function of the relevant chemical potential. So in that case, it's μs. And in baryons, you have the combination of μb minus μs. So somehow the dependence of the pressure on the chemical potential is very simple. It's just given by the cosine function, provided that the mass of the particle is large enough. In other words, you could treat them as a Boltzmann gas. So if that's the case, then it's very easy to construct combinations of different fluctuations or correlations that vanish identically in the hadronic phase. So, for example, if that's a valid decomposition of the pressure, then the difference between fourth order baryon strangeness fluctuations of correlation like 3-1 and second order baryon strangeness correlation should vanish identically, and you could produce another combination which also vanish identically. You can check by straightforward algebra with an errors, and now you could say, well, is this true? So in the sense here, you don't rely on the fact what actually builds up the pressure. It's just the fact that the pressure is given by some gas of uncorrelated hadrons, and you don't really care about what those hadrons are, what their masses are. So that's kind of a relatively simple statement to make. And what you find that indeed, as you would expect, if you have a gas of hadrons, this quantity vanishes identically at low temperature, and at the upper range of the transition regions, they start to increase, and eventually this quantity will reach the value which is characteristic of a non-interacting gas of strange quarks. So somehow here you see how the deconfinement sets in. So up to a certain point, this quantity is very well described by Hadron Resonance Gas, or more generically, any gas of uncorrelated hadrons. And suddenly this description breaks down at the upper edge of the transition region, and you go to the regime where, after a while, where it kind of can be understood in terms of quarks. Again, this region where you go from kind of hadronic description to quark description is wide. So you have like 150 MeV, 100 MeV interval where it's kind of in between. Now, of course, if you look at the strangeness sector, and in particular the strangest resonances, they come from interactions of mesons and strange baryons, so strange hyperons. So you have many resonances, many channels that you can have. So it's not that simple as for the meson gas that I described in the first lecture. But nonetheless, in principle, you could do the virial expansion based on the S matrix in the same way, and it's just a question to what extent you could approximate the virial expansion by the hadron gas. So what has been done is that we took the phase shift from the partial wave analysis by the JPEG group. So that's a joint physics analysis center in JLab, which takes all the data on scattering of different processes and try to do a partial wave analysis to get kind of a phenological estimate or phenological understanding of the scattering processes and the scattering phase shifts. So from that, you could calculate the S matrix. So if once you know the phase shift in different channels, you could plug in and estimate the corresponding contribution to the pressure. Now this quantity here, the derivative of the phase shift with respect to E is the spectral density of your states. And here I show the spectral density for several partial waves that's relevant for strange baryon-meson interactions. And you see it's getting very complicated, and it's not obvious at all if you just can approximate it with a delta function or a Bright-Wigner. So the solid line are kind of the exact phase shifts, or kind of the exact spectral density, just calculated numerical from the available lookup tables. And then when you know where the resonance positions are, you could try to approximate them by Bright-Wigner, which is shown as a dashed line. And in some cases, of course, the Bright-Wigner is good enough. So like, for example, in this green line, but in most of the cases, I mean, the Bright-Wigner doesn't capture very well the spectral density. Moreover, kind of thinking that you could approximate the spectral density by a bunch of delta function is kind of certainly not going to work. So what we did, we just calculated the pressure according to this formula, just putting the phase shift as they are, trying to use a Bright-Wigner approximation, as well as trying to use the standard Hadron Resonance Gas approximation, where you just treat all the resonance as quasi-particle, and we just calculate the contribution to the pressure from these partial waves. And in some cases, it works well, like for example, for D13 partial waves, where all this calculation gives about the same number. But in some cases, it fails miserably, like in the first partial wave S11. Here, of course, the three different approaches give you numbers which are different by a factor of 2 or more, and the same here. So there clearly is a partial waves where the idea of approximating your spectral density by delta functions or Bright-Wigners is totally inadequate. So to some extent, this observation that you could treat the interacting gas by just using a non-interacting Hadron Resonance Gas with zero weights approximation. It's probably too naive. Nonetheless, as I will show in a moment, if you sum over all partial waves, the effect is actually not big. So it's very large in certain partial waves, but overall it's not that large. Yes? Well, they're a lot, right? So for what they put here, they say lambda pion, nucleon. So it's a couple channel analysis. So you have like up to 20 different channels which are coupled. So in fact, when I write in this simple form, I'm always simplifying. It's not just a phase shift. It's essentially a matrix of all the phase shifts, right? And then so it's a real S matrix in a sense. And the basis is typically depending on the partial waves. It could be 5 by 5 or 20 by 20, depending on the partial waves. So it's really large. And of course, they say, well, we need more, but we don't have more data to constrain all these matrix elements. So we have to make some cuts and some approximation in there. But it's really kind of the number of processes you could imagine, or you use, in fact, is pretty large. The baryon interactions, you know them for nucleon, and that's it. And for example, you don't know anything about nucleon. Not quite. Well, nucleon you know actually, but nucleon is not that important. Actually, we included the nucleon, but that's small corrections. What you don't know is, let's say, hyperon-nucleon, hyperon-hyperon interaction. You have no clue what they are. So you only know the nucleon-nucleon. So, and those baryon interactions, which are also important, especially as you go to high density, those are not included here because we just don't know them. Well, there are, I mean, if you look at the spectral density, you don't see any. Of course, when you think about resonance, you can't just look at the spectral density. What you really have to see where's the pole rise, and you could identify, once you do the analysis, you identify the poles, which are complex, sometimes they're far from the real axis, and then of course these guys identified and they give the entire table of the resonances they found, and since you are here, I kind of jumping a little bit ahead, of course they find from their partial wave analysis many more resonances and published in particle data book as well established. So these curves, if you wish, although you don't see them kind of explicitly, they have many more resonances, but you have also other effects like thresholds, right, and continuum, and all these kind of mixed together. So because you have so many channels, kind of fishing out the resonance contribution spectral densities is kind of just looking by that. It's in general it's hopeless. So in some cases you can, and you could even approximate by Figner, but in general you can't. So you really need to kind of look at their tables and look at where the poles are. Yeah, I mean, if you're at low temperatures, you're dominated by one resonance, right? So in baryon-nucleon is slightly different. You have one, the delta is a big resonance. You maybe have some other one, and then you have a large continuum, but the continuum is high enough in energy, so at 130 MeV, it's not relevant. But if you go to 150, then the continuum matters. Here it's kind of more complicated. Here you have kind of non-trivial behavior in the threshold, but again, we are talking about strange baryons. So in total pressure, even the baryon fluctuations, that's a subleading contribution. So this complication kind of masked by the contribution of deltas and non-strange baryons. Well, the phi mesons are always easy because those are narrow resonances and then kind of isolated, always isolated from everything else. So even if it's broad, it's one resonance, and if you do it by bright Wigner, it's probably not too bad. Okay, so now here I show the contribution of strange baryons with the strangeness 1 to the total pressure, which of course is a small number. As I said before, once you do this decomposition of the strange pressure in terms of different meson and different baryon contribution, then of course you could essentially extract these numbers, this partial pressure from the lattice data, right? So if the lattice is described by this one, then this partial pressure can be expressed in terms of different combination of baryon number, strangeness fluctuation, and strangeness fluctuations themselves. So you could, in principle, extract from the lattice also the partial pressure of strangeness equal 1 baryons. And this is shown by this black line. So that's a kind of the partial pressure of strangeness 1 baryons extracted from the lattice given this Hadron Resonance Gas model. And here I calculate the corresponding contribution from the relativistic virial expansion based on S matrix, shown in the previous slides, and that's this black line. And I also compare the standard Hadron Resonance Gas prediction, shown to this dotted line, which uses just PDG states and 0 widths. And you see that once we do the full analysis using the virial expansion on the S matrix, you get a much larger, significantly larger pressure contribution toward 150 MeV or higher. However, it's mostly because this partial wave analysis has more resonances than the PDG. So if you just use a simple Hadron Resonance Gas approximation, but now with the resonances that contain in this partial wave analysis, you get essentially the purple line, and which agrees very well with a black line, which is a kind of the full analysis using the virial expansion and with S metrics. So somehow these different results you're getting in different partial waves kind of compensate each other, and at the end of the result, the Hadron Resonance Gas turns out not too bad. But the presence of these additional states which are not in PDG becomes important. And in fact, if you take the spectrum from PDG and supplement with states which are predicted by Quark model, but not in PDG, you get the same result, and that is shown again by this purple line. And here, again, that's an older analysis, again, shows the same thing. So when you calculate the baryon number strangeness correlation divided by the strangeness fluctuations, you compare with a particle data group resonance gas, you always kind of over predict. And if you include the additional states, these missing states, which are kind of are there in the Quark model, but not in the particle data group, then you get a pretty good description of the Hadron resonance, of the lattice data. Well, I mean, you don't have to treat them on shell, right? I mean, you just say, well, whatever the temperature, there's interacting hadron gas. If they interact, I mean, the only thing you have to assume that somehow the density is not too high, right? And this formula applies. And if this formula applies, and you know the experimental phase shifts, which are the relative of this given by the spectral density, you just plug it in and you get what you get. You don't even need to think about kind of onshore resonances. That's a vacuum, yeah? Yes? Well, to some extent, they are included, right? Because when you do this partial wave analysis, I mean, you have channels which look like lambda star, 15 or 20 times pion. Now, lambda star itself a resonance, so in principle is effectively a three-body, but many of these three-body interaction you could think of as interacting, a narrow resonance interacting with something else. Yeah, but in this case, because it's effectively, I mean, it's not so I'm using kind of, so you have an effective degrees of freedom, which are some resonances, which I didn't put it in. That's already people who did the partial wave analysis treated in this way because they also have their own limitations. So what I'm saying is that although I'm using only second virial coefficient, some of the three-body terms are included. So to what extent these three-body forces and this higher virial expansion are large, it's also, the question is, what's the nature of this interaction? If the interaction is such that effectively some of the three-body look like two-body, and you could constrain them by partial wave analysis, and then you include somehow those effects as well, and that may explain why it works, right? If I would have to really treat lambda star as a two-body system, then that would be much more difficult. To some extent, right? But it's, you see many of those resonances that are there, they kind of have this lifetime and they're very prominent. So if you look how these high resonances decay, I mean, many of them just decay to delta. So in some sense, even delta is not a very narrow, it's an elementary state, right? So what I'm saying is that the nature of hadronic interaction is such that many of these complicated interactions are resummed already. Forget about the Hadron Resonance Gas idea of this virial expansion. You just, in the vacuum already, they factored out. In a sense, they have their own structure, which you could use to your own advantage, because some of the medium effects actually become simpler than what you would naively think. So that, at least from this exercise, was the lesson we learned. That it may be you get some kind of discount in a way. And then, of course, it's again the same with EQCD. I mean, certainly you wouldn't expect it to work, but you do the calculation, which you may or may not believe. You compare with the lattice results, and to some extent, they work better than one might have expected. Okay. And remaining 10 minutes. Okay, so I have a few more slides. So now, of course, you could extend this approach to the charm quark. So you could also calculate different Taylor expansion now involving the charm quark chemical potential and use similar exercise here. Actually, things become slightly easier in a sense that the only contribution you have is charm equal one sector, because if you add another charm quark, the exponential suppression is too big. So practically anything beyond charm equal one sector doesn't contribute. And you could again look at different baryon charm correlation in this case of the fourth order, second order to the fourth order, and etc. And in Hadron Resonance Gas, all these ratios should be close to 1. And that's what indeed we find. But above the transition temperatures, that will be no longer the case. Above the transition temperatures, this ratio starts to deviate strongly from 1, and then you go approach the value which is characteristic of non-interacting charm quarks. Now, if you look at the temperature dependence of different ratios, and here I took a ratio such that you have a baryon charm correlation, which is a proxy for essentially partial contribution from charm baryons. And in the denominator, I have essentially charm fluctuation, we subtracted baryon charm correlation, which is a proxy for meson pressure. So this quantity you could think as a proxy of charm baryon to charm meson pressure. And you could kind of try to compare your lattice results of this quantity with a prediction of Hadron Resonance Gas. And again, if you just take what is known in the particle data group, this is dashed line, and you kind of way under predict what you find on the lattice. But as you include the additional states which are incorporated in the quark model, or appear in the quark model, but not yet discovered, and therefore not particle data group, you get this black line, which seem to agree with the lattice result much better. Now you could go further. So if you assume that charm baryons and charm mesons are the right degrees of freedom in the hadron phase, and you can ask the question, what happens if you go just above the transition temperature? And here again, compared to the strange or light quark case, the situation is simpler because the charm quarks are always heavy, so they always have the mass much larger than temperature. So in principle, you could use a Boltzmann approximation also in above the transition temperature where you have quark degrees of freedom. And in most general, you could think rewriting the charm, partial charm pressure as a contribution from charm quark, charm baryons, and charm mesons. And of course, the chemical potential dependence, as usual, in Boltzmann approximation, factors out and is given by these cosine hyperbolicus factors. So now you could, once you have this ansatz for the pressure, you could calculate different fluctuations and correlations. For example, you could calculate the charm fluctuations, baryon number charm correlations at fourth order, 1, 3, and 2, 2. So you have 3 different quantities, for example. From these 3 different quantities, once you calculate in this form and on the lattice, you could kind of invert the relation and using the lattice data on these 3 quantities, estimate the contribution of charm quark pressure, charm baryon pressure, and charm meson pressure. And just look how they depend on the temperature, and that is shown here. So what I show here is essentially this partial contribution of charm meson, charm baryon, and charm quark pressure inferred from the lattice data, normalized by the total charm pressure, which is just given essentially by, for example, the chi2c. So what you see here is, in the red, is what you would call the partial charm quark pressure. And you see that close to the transition temperature, it has large errors, but it's compatible with large errors within zero. And this contribution of charm quarks to the pressure increases as you increase the temperature, as you would expect. Eventually, at temperature around 300 MeV, most of the pressure is due to charm quark. Now, if you look at the charm meson pressure, or divided by the charm pressure, so normalized by the charm pressure, it has the opposite tendency. At low temperature, it's essentially the dominant contribution to the pressure. And as you increase the temperature, it decreases and eventually goes to zero. And the same is true for baryonic pressure component of the total charm pressure. It also, it's smaller, of course, but it's sizable around the transition temperature. As you go to above the transition temperature, so it decreases, but it's not kind of instantaneous going to zero, kind of decreasing very slowly. So, for example, if you consider 200 MeV or 190 MeV, then a significant part of your pressure comes also from charm meson and charm baryons. So essentially at 170, 180 MeV, half of your pressure is due to charm quark and half of the pressure is some other degrees of freedom, which in this simple model you would identify as a pressure of charm mesons and charm baryons. And of course, at low temperature, this partial pressure of charm meson and charm baryons seem to agree with the prediction of the Hadron Resonance Gas. So this analysis kind of shows that if you are not kind of very far from the crossover temperature, but you're somehow close, but above, like 180 MeV, 170 MeV, somehow, if you want to understand the charm degrees of freedom, then certainly the notion of charm quarks alone is not sufficient. You need to allow additional degrees of freedom about TC, such as charm mesons and charm baryons. Okay, so now if you have the Taylor expansion, you could also calculate the pressure now at non-zero baryon density. And what I show here on this figure is the difference between pressure calculated at finite chemical potential, baryon chemical potential, and zero baryon chemical potential as a function of the temperature. And what you see and what you expect, of course, to some extent, is that as you increase the temperature, the kind of extra baryonic pressure, so the difference between pressure calculated at finite baryon chemical potential, zero baryon chemical potential increases, and eventually it approaches a value which you would estimate from the Quark gas as well. At low temperature, again, this partial baryonic pressure, or the correction to the pressure due to finite chemical potential, follows the Hadron Resonance Gas model. Now, here I show a consecutive order, so you could calculate different truncations. You could calculate this partial baryonic pressure, or the correction due to finite chemical potential to the pressure at leading order, mu b to the squared, that's of the red line, fourth order and sixth order. And you see this, unless you have baryon chemical potential of order the temperature, where the leading order is good enough, you typically need to go to the fourth order. But from the fourth order on, you don't see much correction. So the fourth order captures most of mu b dependence of your pressure. And at least up to chemical potential, something like smaller than 2.5 in units of the temperature, the fourth order correction is good enough, and fourth and sixth orders are more or less the same. So up to this chemical potential, essentially the sixth order Taylor expansion seems to converge, at least apparently. Now, if you have that, you could also try to estimate the convergence radius of your Taylor expansion. So, so this Taylor expansion of the pressure of course, has a finite radius of convergence. And if all the expansion coefficients are positive for some temperature, and that seems to be the case for temperature smaller than the transition temperature, then the singularity that limits this radius of convergence lies on the real axis and may be identified with a critical point. So now, of course, if you estimate the radius of convergence, you could do it either in terms of the pressure or in terms of the baryon fluctuation itself. So you could provide different estimators. So here is one possible estimate of the radius of convergence. And this estimator has been kind of evaluated in the lattice because it's dominated by 6th order, which is very noisy. We just could kind of give an upper bound, and that given in the shaded yellow region. So everything, so that's a function of the temperature, and essentially that is the radius of convergence, which would give you an estimate of mu be critical. And you see that everything below this blue line is essentially where you see apparent convergence. So everything in this blue region is yellow region below this blue line is something where a region where the location of the critical point is disfavored, because at this region you know that the Taylor expansion converges. So at least what we could say from currently from the lattice results on the Taylor expansions, that the existence of critical point for mu b smaller than 2t is disfavored by testing lattice data, but of course that's based on truncating the Taylor expansion 6th order, so you always have this problem that you try to make an asymptotic statement based on very few numbers in the expansion. So there is this caveat. Okay, so my time is up more or less, and I stop here and please ask questions.
Hello. In the previous slide, you showed the charm pressure, quark pressure, and Mason pressure.
Right.
Yeah, this one. So the Mason pressure and baryon pressure are high at low temperature, and quark pressure is high at higher temperature. Does this indicate deconfinement?
Yeah. So you may say that. Well, I mean, the deconfinement you could think of as changing degrees of freedom, right? So you would say deconfinement means that the dominant degrees of freedom are quarks, and confinement means the dominant degrees of freedom are hadrons, and essentially that figure shows this very effect that if you go to the transition temperature, there's a quark pressure with a large error, but it's compatible with 0. And of course, the pressure is dominated by baryons and mesons. So that's what you would expect. Now, I guess what may be interesting is that the way this meson and baryon pressure kind of turned off as you go to high temperature is not very abrupt. It's kind of very smooth, right? So you go to higher and higher temperature, and the meson pressure is still significant, right? So it's not that, well, the fact that the meson pressure would essentially go to 0 at high temperature, that you would expect. The fact that it does so relatively slowly may be an interesting result, which has thermological consequences, because it tells you that if you, even above the transition temperature, but somehow close to it, you can't think of having only charm quarks in the system. Somehow you need to think of having charm baryons. So if you, for example, think about what flows, what does charm flow means, you usually say, well, up to TC is essentially only charm quarks that are flowing, right? But it's not completely true, because charm quarks are only part of your total charm. You must allow that you have some other degrees of freedom, or meson-like degrees of freedom, meson-like excitation, which flow as much as charm flow do. So it's kind of now you need to rethink how you treat the flow of charm quarks, let's say, or charm degrees of freedom in Quark-Gluon Plasma. Because until now it was always charm quarks, and then you hadronize at TC, but what this picture shows, that's not quite correct.
So even beyond the transition temperature, charm quarks, charm mesons are possible.
Charm hadrons are there. Well, something like this, it don't have to be the same D mesons or lambda C baryons that we know from PDG. There's some kind of broad excitation, but they're there, cannot be ignored because they contribute significantly to the total charm.
Okay, in quark number fluctuations at high temperature slide, the plots were against susceptibilities with temperature. Yeah. So, yeah. So maybe it is a very naive question, but how do we get idea about the fluctuations from these susceptibility ratios?
I mean, the susceptibility is what they are, right? So you calculate them on the lattice, and of course, by just looking at the figures, the fact that they are close to 1, it tells you that it looks like something like quark degrees of freedom, right? Because if you're hadrons, I mean, they will be much smaller, completely different. They will be somewhere here. Now, the question what we're asking here is, okay, I mean, they look like they correspond somehow to a quark gas, but the quark gas is still not interacting, right? It's not an ideal quark gas. And can the interactions, which we calculate in perturbation theory, explain quantitatively the lattice data? And what I'm trying to say is that to a large extent they can. Right? So the fact that this fluctuation of U quark somehow correspond to quark degrees of freedom is obvious from the fact that they're close to 1. This is close to 1, this is close to 1. So 1 means, well, because the scale is different, but essentially once you're close to 1, you would say naively at least that it's quark degrees of freedom we are talking about, because asymptotically it should be 1. Now the question, well, it's not exactly 1. Do we understand the deviation from 1? And the question we do. Here, of course, the same thing, right? You look at the U and D quark correlations, and if you have an ideal quark exactly 0, of course, if you have any interactions, it won't be 0. And now this small non-zero value can be understood quantitatively using weak coupling expansion, and again, the answer we can. So here, everything about quantitative features. Qualitatively, if that is 0, that is close to 1, you would say, well, it looks like quark gas, and now you need to verify to what extent or how well you can quantify this.
Okay, so in that interaction picture, when you were talking about that non-resonance meson-baryon interaction, and we found out all those phase shift, so does someone just can become interested in that resonance interaction between them? Suppose when we are talking about that pi plus pi minus interaction, we talk about rho channel and all those kind of channel, resonance channel. But okay, now if I doing the HRG and go to higher temperature limit, is it possible that the interaction between resonance particles also will be take account? That means suppose I have a lambda-lambda interaction.
Well, I mean, if it's a ground state lambda, then of course it's still, you're talking about ground state. Now, in some sense, if you have interaction between two broad resonances, that would be like a 4-particle interaction, and that would go into higher virial coefficients, which we don't take into account. Now, as I said when Raju asked the question, of course, in reality, when some of the interactions that you put in your partial wave analysis already assume that a narrow resonance interacts with something else, which effectively is 3-body, but here is treated in 2-body way. So to answer your question, in the analysis which I just showed, in the stranger sector, at least some interactions where a resonance interacts with a stable particle is taken into account. Effectively, it's 3-body, but we treat it as 2-body, and that's in there. But of course, there could be kind of even more complicated interaction which are not included.
So
the ones you have in mind, resonance interaction, like say rho, is never included because we don't know what it is. And most likely, you could only include it if you go to higher order in virial expansion.
So in the first lecture, you were talking that, okay, we can mimic all those kind of attractive interaction after the inclusion of our HRG model. But okay, those interaction all between non-resonance particle. So,
so that's right. I mean, so if you have a meson gas, then it's simple. You have kind of stable particles, pions and kaons, right? And they interact, and there's also interactions like 90% are resonant and kind of well-separated resonances.
But just after lambda cascade, or when we
but once you have the lambdas, or you have more complicated, so for example, strange baryons, we have more channels, then it becomes more complicated, right? So then this idea that all interactions just well approximated the resonance is just not true. Okay. That's what I was trying to tell, and it's just the nature of I mean, if you look at the phase shift, and you see kind of two nice phase shift going through pi's, and of course that tells you that. So here, of course, they have kind of all interferences. They don't have such nice figures. So it's just that somehow the meson-meson interaction in some sense simpler than baryon-meson interactions.
Thank you.
When we plot this energy density by temperature and T to the power 4, P by T to the power 4, those
This one?
Yeah, any plots of energy density by T to the power 4 or P by T to the power 4, you have said those are for more than one flavor.
So that's 2 plus 1. So it's light quarks.
Yes. So how do we take care of the abundances of their each quarks and different types of flavors? I mean, number of up quarks are not probably same as the number of charm.
Well, I mean,
way to take care of those things.
Yeah. So you do. Well, it's what you put in the lattice calculation. So the lattice calculation we are usually doing are you put on in your Lagrangian, you assume you have 2 light quarks, so U and B, which are degenerating the mass, and you have a strange quark mass which is heavy. So that's what you put in the Lagrangian. That's what goes into your simulation. Now, of course, from the beginning, you could put in assume that the Lagrangian contains a charm quark, and you put it in from the very beginning. So it's not like while you're doing the calculation, you're putting it in. You're putting it in essentially in your computer code. So you have an input file, and then you dial in that I want NF to be 2 plus 1 plus 1 or 2 plus 1, and I give the quark masses what whatever values they need to be. Of course, I have to do it at 0 temperature first, so I know what I have to put in the quark masses, right? But it's kind of there from the beginning, and you could put as many flavors as you want in principle.
Yeah, but their number of particles of each flavor are different.
Well, I mean, the number of particles is not something which is defined, right? I mean, if you are at 0 baryon densities and the net charm content of your system is 0, right? You have charm particles, charm antiparticles, so that it adds up to net 0 charm. But of course, it's this temperature decides effectively how many you have, but it's not kind of something that you have a control over. So talking about a fixed particle number in the relativistic system doesn't make sense, right? Because a particle or the chemical potential couples to conserved charge, not to particle number.
So we don't need to put some ratios by hand. The temperature takes care of that.
The temperature takes care of it. We only have to say how many flavors do we wish to have in our simulation. So how many flavors do we have in our Lagrangian that you put on your computer, and whatever the rest comes out. But of course, it's not even easy to define how many charm quarks you have, right? I mean, it's not a well-defined question if you have a system.
Other question? If not, thank the speaker.